Okay, today we're going to start with the special matrices and the matrices and the Lagrange interpolation. Okay, first we start with the determinant of the Vandermonde matrix. The 4x4 Vandermonde matrix looks like this, and determinant of this Vandermonde matrix is like this. If you see, then here B minus A, C minus A, and D minus A times C minus A times D minus A, C minus B, D minus B, and D minus C, like this. There are three terms with minus A's on back, and two terms with minus B's on back, and one term with minus C back on the back. If you generalize it, then we see this matrix, and this is determinant. This is the general size of Vandermonde matrix. The determinant of this matrix looks like this. This is what we're supposed to prove. As you see, it is like the product of xn minus xn minus x1 times xn minus 1 minus x1 x2 minus x1. So there's n minus 1 terms like that. And the next terms, we have n minus 2 terms and with minus x2. And there's n minus 3 terms and with minus x3, and so on until the xn minus 1, which is one term. So it's a triangle with the triangle forms of those terms. If we write it in one presentation, that it can be written in this way. Okay, so we can generally guess the general form of the determinant of the Vandermonde matrix. The proof is can be done by mass induction. So when the size of the matrix is equal to 1, then it is trivial. There's only one term, which is 1, so it's done. We assume this equality is true for n minus 1, which is the size of the matrix. Then when the size of the matrix A is n minus 1, then assume that we have this equality hold. Then we show it is also true for the size of the matrix N. Then we know the determinant of A is same as determinant of A transpose, which is this. So here, if we multiply minus x1 on the first row and add it to the second row, then we will have the this second row. If we multiply minus x1 on the second row and add it to the third row, then we will have the third row in this form. If we multiply minus x1 on the third row and then add it to the first row, then if we multiply minus x1 and subtract it, then we will have the fourth row, and so on. So we will have, if we do this elementary row operation on this matrix, then we will have this. Since this is a third type elementary row operation, it doesn't change anything on the value of the determinant. Then we have all 0 terms on the first column except the first one. So we, by using the cofactor expansion, then the determinant of this matrix is same as determinant of this. here, do you see, we have a common factor, x2 minus x1 on the first column. And we have x3 minus x1 as a common factor for the second column. And xn minus x1 on the last column. So we can factor all these out. Then we have x2 minus x1, x3 minus x1, and xn minus x1, and times the determinant of this smaller size matrix. But we assumed by the mass induction, the determinant of this matrix is given as this. So if we can write these terms all together in this way. So determinant of A is the product of ij is equal 1 to n, where when I is bigger than j and xi minus xj. So we have n times n minus 1 over 2 terms of those, which is the value that we are looking for. The important thing of this are, this determinant cannot be 0 if these xi's are all different. If xi is not same as xj for all I and j, then these are not 0. So product of non-zero terms should not be 0. What this means is, if we do choose this x1 and x2 and x3 up to xn on the x-axis as time goes, then this matrix never be 0. So this matrix always have the inverse of this matrix. We can easily find a way to compute this determinant in various ways. Now I explain how this van der Monde matrix is related to the curve fitting. Suppose we have data which was described from the experiment at the chemistry or biology lab or engineering lab. First, we assume xi is not same as xj. And then we have a data x1, y1, and x2, y2, and xn, yn. Then we may think of a linear equation, y equal a plus bx, that best fit on these data. Okay. Then we may think that this equation satisfies all those points. So y1 is equal to a plus bx1, and y2 is equal to a plus bx2, and yn is equal to a plus bxn. If this line passes through all those points, then it satisfies all these n equations. If we rewrite it in the matrix form, then we can write it as mv is equal to y. Here we think this M matrix first. Then, since xi's are not same at all, so this is not the multiple, this second column is not the multiple of the first column. So this is a rank 2 matrix. So it has a full column rank first. And V can be written this way, and Y can be written as a vector, n by 1 vector. Then, this linear system of equation, when we multiply M transpose on both sides, we have M transpose MV is equal to M transpose Y. Important thing is, what's the size of this M transpose M? What's the size of this matrix? Ms. Chung? What's the size of this matrix? M transpose M. This is a 2 by 2 matrix. But this matrix M has rank 2. So this is a 2 by 2 matrix whose rank is 2. We know the rank of M is same as rank of M transpose A. That's what we show in the earlier stage of our class. So this is a 2 by 2 matrix whose rank is 2. So this is an invertible matrix. So we can find the inverse of this matrix. So V can be found just multiplying the inverse of this matrix M transpose M. So we have V now, A and B. What that means is we have Y equal A plus BX. And this A and scalar AB can be found in this way. That means we were able to find a linear equation that best fit this endpoint. Okay, here we call this line. This line is a least square line of best fit or regression line on those data. Okay, we can extend this knowledge to the higher order of polynomial. Suppose we have the M data, M point from the experiment. And suppose we are looking for a polynomial of M, polynomial of degree M that passes through these points, these N point. Then, okay, this polynomial of degree M should satisfy all these points. So we just plug in xi's and yi's on every lines, on those equation. Then we have a linear system of equation like this. Okay, if we write it in a matrix form, then it can be written as this matrix times this vector is equal to y. That is MV is equal to y. Okay, here this is the matrix M, whose size is n by m plus 1, isn't it? Here, 0, 1, 2, m. So this size, it has m plus 1 columns, and it has n rows. So this is n times m plus 1 matrix here. The important thing is, as you see here, suppose xi's are all distinct. If the experiment was examined that when time is 1 hour, 2 hours, 3 hours, 4 hours, and like this. If the experiment was checked that every day at this exact time, then suppose we have 30 days who has the experiment, then we have the 30 point that makes the size of this matrix about 31 with 31 columns. Anyway, so then if xi's are all distinct, we know these columns are all linearly independent. So when we multiply M transpose A, when M transpose on both sides, still this M transpose A is a matrix having full column length. So this is an invertible matrix. See, so we can find the inverse of this matrix and multiply it in here to get V, which are the AIs, which makes the coefficient of the polynomial that we are looking for. So we have, with this simple mathematical model, by using a couple of basic properties on the linear system of equation and matrix, we can easily find the polynomial of best fit. This process is called the Lagrange interpolation. And this matrix is the one that is a special case of the Van der Monde matrix that we mentioned. So Van der Monde matrix are used in the Lagrange multiplication in this way. If we go to a website here, then we can give a certain point. Suppose we give a 2 point, then this is the equation of the best. This is the least square polynomial that passes through these 2 points. Suppose we give a 3 point, then this is the Lagrange interpolation which was obtained by the algorithm that I showed you. This, and if suppose I'll give me one more point, then this is the polynomial of degree 3 that passes through 3 points. Suppose I give another point, then this is the polynomial of degree 4 that passing through 5 points. If I give one more, then this is the polynomial of degree 5 that we get from the same algorithm that I showed you, passing through 6 points. So this can be done in this way. You understand? Ms. Hong, you got it? But if I give some more point like this, then we you see here I gave about 36 points, but I want to have a polynomial of reasonable degree. I don't want to have, even though I have 1,000 points, I don't want to deal with the polynomial of degree 999. So if I can always restrict the degree of the polynomial that best fits on those points from the experiment. So still I can find the best approximation of it with this Lagrange interpolation algorithm. So this is what you're supposed to know. And next, the matrix representation of linear transformation. You should know each linear transformation has the unique one-to-one correspondence to a matrix. Okay, so when we have a linear transformation T from a vector space Rn to vector space Rm with the basis alpha and beta respectively, then we can always find the matrix representation of this linear transformation T with respect to this ordered basis alpha and beta. This matrix can be written in this way. Then how we can find these AIs or this column vector of this matrix representation? This can be done by this algorithm. Suppose if we have a T, then we can think of the image of the xi's from the basis element of Rn. Then we can write the image of xj under T as the linear combination of this basis beta in Rm. Then we can find these Aij's. With these Aij's, we can form a column vector A1j, A2j, and Amj, like this. This is the coordinate vector of T of xj with respect to the basis beta. So we can write in this way. We can fill out the jth column of A prime with this vector, these column vectors. So for the first one, we write the coordinate vector of T of x1 with respect to beta, and coordinate vector of T of x2 with respect to the basis beta, and so on, up until the coordinate vector of T of xn with respect to the basis vector beta. Then each of these columns makes a matrix A prime. Then this matrix is called the matrix representation of T with respect to the basis alpha and beta, from alpha to beta. Okay. Okay. The one important fact is the form of this matrix A is not same as the matrix A prime, but these two matrices A and A prime for these different bases. Here is a standard basis, and here the basis alpha and beta. This matrix looks different, but they have a very close relationship, which is called the similarity. Okay, so these matrices are not looks the same, but they are a very close class of matrices, which is called the similarity. Okay. Okay. So you should know how to find it. But in the real problem, all you have to do is just solve. Can be done by solving the linear system of equation. You know, T of x1 looks like this. This should be written as the linear combination of yi's. All you have to do is find this a1 and a2, and b1 and b2, and c1 and c2. So if you combine all those, that's just solving the linear system of equation. So if you know how to solve the linear system of equation, then this mathematical modeling of the given problem on finding the matrix representation of the linear transformation can be done. Okay? So you should be able to do it. Okay, here the example shows how this exact computation can be done. Okay, next. There are many problems that you should know. You should be able to teach it to your student. And there are several other problems which you are familiar with, and you should know. And there's a concept of minimal polynomials and generalized eigenvectors. And you should know how to prove A is similar to A transpose. And there are many interesting facts, not only on the determinant, but also there are many interesting facts on other matrix functions, such as the joint. Compound. We already mentioned Sylvester-Franke theorems and the property on the compound matrices. And now, the canonical forms. Jordan canonical forms. You should know. Okay. Yeah. When we deal with the mathematical models, so we start from the real life problem, then we will draw the mathematical equations from that. Then we translate it and we linearize it to the linear system of equations. Then we have the big size of matrices is involved in that linear system of equations. Since it also will involve the sophisticated and long computations to do to solve that linear system of equations. We would like to simplify that linear system of equations to a form which we can easily deal with. So by Schur's theorem, it is not difficult to think or prove it in the form of the triangular matrices instead of the normal rectangular matrix. But even though it involves the triangular matrix, we still need a lot of long computation. So we like to go a little further. If it is a diagonalizable matrix, if the matrix is a diagonal matrix, then everything goes very easily. But not every matrices are diagonalizable. So we should find a way to find the canonical form, which is very close to the diagonal matrix. Let's say it's a block diagonal matrix, and then we simplify it as much as it can be. One example of those canonical form is the Jordan canonical form. Okay, that's what is written here. Okay, yeah. If a matrix of square matrix has a full linear independent eigenvectors, the full set of linear independent eigenvectors, then it is diagonalizable. In that case, it's very simple. If a matrix is a normal matrix, then it is unitary diagonalizable. So it can be done easily. But there is a matrix, diagonalizable matrix, even though it is not a normal matrix. Okay. So for all such questions, for the general case, this Jordan canonical form gives us an answer. This is one nice canonical form. Okay. This is the shape of the Jordan canonical form. Jordan canonical form of A. When Ji's are block diagonal matrices. When this Ji's has these forms. Is an upper triangular matrix whose super diagonals are ones. We call this is a Jordan block. This is a one Jordan block corresponding to the eigenvalue lambda I of A. Okay. And this JA is called the Jordan canonical form of A, which is the direct sum of these Jordan blocks. Okay. So all we have to do is find from the given matrix A, find all Jordan blocks, then makes a direct sum of it to get the Jordan canonical form. Okay. Okay, so from the given matrix A, how to find the Jordan canonical form of the given matrix A is basically follow the following step. First, we find the eigenvalue of the given matrix first. Then, for each eigenvalue, we found the Jordan block of A corresponding to each eigenvalues first. The way of doing so is checking the rank of the matrix A and the rank of A minus the particular eigenvalue lambda I. So rank of A minus lambda I. Then we find the rank of A minus lambda I times identity to and the power of that matrix and cube and so on, then the difference of those lengths give us the number of Jordan blocks of A corresponding to the eigenvalue lambda I. That give us the dot diagram of this form. And this dot diagram give us the exact number of Jordan blocks for each corresponding eigen values. This makes this theorem. And all of this process, so suppose we found, we have the matrix A here, then we first find the characteristic polynomial of A first. Then there are two distinct eigenvalues. For the eigenvalue 3, yeah, we have only 1 point in the dot diagram. So we have just 1 by 1 Jordan block corresponding to eigenvalue 3. But for this one, for eigenvalue 2, which has algebraic multiplicity 3, so we have to check it. Then we check the length of A, the size of the matrix and length of A minus 2i's. The difference between those two, the size of the matrix and length of A minus 2i, give us the R1, and length of A minus 2i minus length of the square of A minus 2i give us R2. That give us R1 as a 2 point and R2 as a 1 point, which give us 1 2 by 2 block and 1 1 by 1 Jordan block, which has 2 by 2 1 block, the 1 by 1 Jordan block corresponding the eigenvalue 3, and 2 Jordan block corresponding to the eigenvalue 2. One is 2 by 2, one is 1 by 1, which comes from this Jordan, these dot diagrams. All this process was explained in detail with all the problems that was treated in the elementary linear algebra book of mine. And if you go to the YouTube and search it, the Jordan canonical form at Seongyungan University linear algebra, then you will be able to find this chapter 10, Jordan canonical form problem solving by Mr. Shin. And if you go here, then you will see how most of the problems in the textbook was solved by the freshmen
이건가?
university.
이제 우리 마지막 챕터
Okay, so if you want, you can go back there to look over the freshman student, how the freshman students solve those problems. Okay, and the next. After you found the Jordan canonical form, then we need to find an invertible matrix Q such that A is equal to, Jordan canonical form is equal to Q inverse A Q. So how we find this matrix, this matrix P or Q, so which makes the P inverse AP is equal to the Jordan canonical form of A. Similarly, this process is called the finding the generalized eigenvectors. So, suppose we have the Jordan canonical form of A first. Suppose we have A matrix A, then we can find the Jordan canonical form by hand or by using any mathematical tool to get the Jordan canonical form A first. Then the method of finding this invertible matrix Q is not unique, but this is observation that give us the possible algorithm. So I explained that how the observation on how to make this algorithm to produce the generalized eigenvector for each of the distinct eigenvalues. So from the first we found the Jordan canonical form of A, then from there we are looking for the columns of Q, this invertible matrix Q that satisfies this property, and this then these columns of Q should satisfy these conditions for distinct eigenvalues lambda j's. So then we have, if we have the a certain number of linear independent eigenvectors for the corresponding distinct eigenvalue lambda j, then we can construct other number of independent vectors from the given linear independent eigenvectors to fill out the empty spot of the remaining columns of Q. And if we then this concludes the algorithm. Okay, if we rewrite the algorithm, then first find the algebraic and the geometric multiplicity of the given the eigenvalues of the given matrix. Then we find the Jordan canonical form first. Then for each Jordan block for the corresponding eigenvalue, then we have a clear view of the structure of the Jordan canonical form of A. Then for each Jordan block, we just concentrate on each Jordan block. Then we know exactly the size and the lambdas, the diagonal entries, and we have a super diagonal entries as well. Then from the one linear independent eigenvector, then we produce the number of linear independent vectors from the given linear independent eigenvectors to feed out the invertible matrix corresponding to the each Jordan blocks. And then after we find the Jordan the columns of the matrix Q, then we make a direct sum of those matrix Q to the submatrix of Qs to form a n by n invertible matrix Q, then check whether that's the right one or not by just multiplying AQ and QAJ to be same. We check it. Then here is the example. So suppose we have the matrix A, then we find the eigenvalues and find the linear independent eigenvectors first, and then we know how many generalized eigenvectors is needed for each Jordan block. Then we use that algorithm to generate the necessary number of generalized eigenvectors to fill out the columns. Then we can check. Then we can get the matrix Q like this. Then we can check AQ is equal to QJA when J Jordan canonical form is like this. You can see they are checked. They are same, which shows Q inverse AQ is equal to JA like this. Okay. So these are the other examples which was treated. Okay, the last chapter of this lecture covers the second part on the canonical forms, which deals with the properties of Jordan canonical form, the blocks of Jordan canonical form and Jordan block, and the properties on block matrices, and some consequences of Jordan canonical form and the Jordan blocks, and the properties of Jordan blocks, and the strictly upper triangularizable matrix version of Jordan canonical form. So makes using the analysis technique on matrix theory. And this is what I mentioned. This fact is what I mentioned. The number of Jordan blocks with the same eigenvalues is exactly same as the geometric multiplicity of that particular eigenvalues. Actually, this is the number of linear independent eigenvector corresponding to that particular eigenvalue. Okay. The proof is very simple, like this. And if A is diagonalizable, then geometric multiplicity of each eigenvalue is the same as algebraic multiplicity of each eigenvalues of A. And there are other versions of Jordan canonical forms, and there's the unique. This theorem shows the uniqueness of the Jordan canonical form if we give the order of the Jordan blocks by using the permutation matrix, and also we can manipulate the Jordan canonical form for our own need in various versions. So there are many things that can be listed. We can, with this knowledge, we can always simplify the linear model that we have after the linearization process to before we use the system into the computers to do the computation. I think that will end today's lectures. Any questions?